We now want to talk about fitting something that's, let's say, more sophisticated than just a simple line. Okay, and so for instance, we could think about fitting a parabola or a quadratic function through data, or a cubic. Okay, depending upon your data, you may want to do something more than just what a line is. Okay, so we also have data that might be exponential, and in fact, there's some tricks for doing data linearization that I'm going to show you right now. So in general, if you have something that's maybe more complicated polynomial, let's think about a function. How about something like this? Perfectly reasonable function. It's now got a quadratic term in it, and now you want to determine a, b, and c. Now before, we only had 2 coefficients. Now we have 3. The process of what we did previously holds here, which is you're still going to look at this error, which is the sum of your function minus the actual data points squared. Okay? And now your function is going to be this here. So now instead of just looking at this e, which is now a function of a, b, and c, that is the fact now that this function has all 3 parameters in it. In order to find the a, b, and c, you do exactly what you did before. But now, there's one additional parameter, which is this c. So you minimize that error with respect to these parameters by just simply computing the derivative, and it's a very simple process to do. And what this results for you is not a 2x2 system, but now you have a 3x3. Linear system of equations that is easily solved using whatever method you'd like, okay? So that's the kind of general process if you're going to do polynomial fits. If you have an nth order polynomial, you get an n by n system of equations to solve, okay? So whatever that polynomial is, you can calculate what the matrix looks like from these terms here. You might also want to think about fancier fitting, which is something like, well, what happens if my data, which is often the case, maybe has some kind of exponential behavior. Okay, so for instance, you might have a biological model where you're modeling population growths, and a lot of population growths, at least for some time before they saturate, have sort of this exponential behavior. And so you wouldn't want to be fitting it to a linear function. You'd be wanting to fit it directly to something like this exponential. Now the problem with fitting it to an exponential here is that you no longer get a linear system of equations out for instance, these 2 parameters, c and a. In fact, if you look at the error now, this e, you could say this thing here now is a sum c e to the ax minus y of k, that's k, squared. Okay? So I just took the formula, plugged in my fit that I want to do. And the problem with this is now when I start doing derivatives, in particular this one here, what happens? Now the 2 comes down, so I get a sum 2 c e to the a x of k minus y sub k times the derivative of this thing with respect to a, which gives me back c x of k e to a to the x of k. Oops, sorry, went off the edge there, times c x of k e to the a x of k equals 0. And now the problem is I don't get a linear system of equations for a. A is sitting up in the exponent. So what I get is a nonlinear system of equations. And here's the problem with nonlinear systems of equations. You don't know if there's one solution, two solutions, infinite solutions, no solutions. There are no guarantees about these nonlinear system of equations. And so what you're actually ending up doing in something like this is having to solve something that you don't know how many solutions might exist to this thing, okay? If any. So that's the real problem here. Soon as you make a function here that's not a polynomial, this method creates problems for you. Of course, there are ways to solve nonlinear systems of equations, and we'll talk about that in the third lecture. And often those are related to iterative techniques where you try to guess a solution and you hope it's close, and then you use a Newton method to try to find the solution and converge to the solution. And we'll talk about that sort of in the third lecture of this. But for the most part, this is kind of a disaster. However, at least if you're looking at exponential data like this, there is a trick that's available in Excel as well, or in most of the packages that are trying to say, if you look at most packages that do line fits or curve fits, they'll do polynomials and they'll do exponentials for you very easily. And all this trick involves is redefining your data. So instead of looking at your data set, which is xk, y sub k, you look at a different data set. You define a new variable, capital Y is a log of y. Now notice what this is going to do. It's going to take my data, and if it's really exponential data, the log and the exponent undo each other, right? So you know that the log of e to the x is just x. So it takes an exponential function and it turns it into a linear function. And that's going to be the key here, is to define a new set of variables where I've linearized the data. Okay? So what I want to do here is define a new variable, capital Y, capital X, which is just little x, and b, which is log c. So I'm going to take my original problem, which is in terms of trying to fit it to c e to the ax, and I'm going to try to now take my data and my data points, turn it into these new variables, capital Y, capital X, define b to be the log of c, and then what you're going to find is that if I now start to think about the log of y, but y itself, remember, is I'm trying to fit it to c e to the ax. Well, my log rule says that, well, that's natural log c plus natural log e to the ax. Log of c, oh, look at that. That is b. That's what I just defined here. Plus log e undo each other, and you get ax. And remember that this is y. And so now what I've essentially done is I've made a transformation into a new set of variables, capital X, capital Y, where I'm going to do a line fit. And I know how to do a line fit. That's easy. Then I solve a 2-by-2 equation for the capital A and B. Once I get capital A and B, I can just come back through this process. Okay, so essentially what this does is by taking the log of your data, if you're going to do an exponential fit, take the log of the data, and you find yourself with a linear least square fit problem to solve. Okay, so these are some tricks that you can sometimes use to actually solve problems that are in fact not linear.